We are live.
All right. All right. Thanks everyone for joining. I am here today to show you another Moonbuilders workshop. I think I haven't done one of these in a while. So today we're actually gonna talk a little bit about how Moonbeam extends the EVM compatibility and adds sort of like extra features on top of that, including interoperability. And we're also going to focus it actually to one precompile contract that we launched very recently called the batch precompile. So yeah, thanks for joining. By the way, my name is Alberto, and I lead developer relations at Moonbeam. So yeah, let's jump right in. So I'm going to go ahead and share my screen. Today it'll be only me, so we don't have any guests. It'll be me hosting, me doing the workshop and everything. So hope you enjoy that. So all right, I prepared. So in today's presentation, we'll do. Hopefully, you can see my screen well. I think you do. And what we're going to do today is go through some slides that I prepared. I have the link to the slides at the end of the presentation. And also, I prepared a little bit of a demo to show you the power of the batch precompile, right? So I guess we can just jump right in. As you can see, today's presentation is called Expanding Moonbeam's Ethereum Compatibility with Precompiles. Like I said before, my name is Alberto, and I work at developer relations on Moonbeam. So the agenda, it's going to be pretty straightforward. I'm going to start with a little bit introduction to Moonbeam. What is it and why is it special? This is a slide that I've used in other presentations before. Next, we have the frontier part, which talks about our Ethereum compatibility layer. And this is important to understand a little bit of a difference between, smart contracts, regular smart contracts, and precompiles. And last but not least, we're going to talk about precompiles. What are they? A few examples. And we're going to focus this presentation, as I mentioned before, on the batch precompile, which was recently introduced to Moonbeam Moonriver and our testnet Moonbase Alpha. If this is the first Moonbuilders workshop you have joined, in Crowdcast, you have an Ask a Question button. So the way that I like to do it is that if at any point you have a question, feel free to use the Ask a Question button. And as I go through the presentation or the demo, I'll try to pause and see if there's any relevant questions, and so we can move forward like that. So yeah, I mean, the first question is, what is Moonbeam? And hopefully by now you're familiar with our project. But if you're not, this is going to be a very brief introduction of what is Moonbeam. So within the Polkadot or Kusama ecosystem, Moonbeam or Moonriver provides an Ethereum-compatible smart contract platform for the entire ecosystem, right? So in the right-hand side, you see sort of the familiar EVM thing as a base layer for Ethereum compatibility, but we have added layers of features to provide sort of extended things outside of the EVM layer, right? For example, the first layer is that we're built with Substrate, which is an SDK sort of to build blockchains that can easily connect to Polkadot. And the main benefit of this is to have native interoperability and basically benefit from the shared security that Polkadot provides. Another layer of added benefits that you have is that we have a full Web3 RPC support, meaning that you have seamless ETH-JSON RPC integrations. And we're going to talk a little bit more about what is the ETH-JSON RPC, right? But the main idea here is that because our integration is seamless, tools such as MetaMask, Ethers, and other development tools can work right out of the box on Moonbeam without any modifications. Another one is unified accounts, meaning that Substrate-based blockchains usually have a different account scheme than Ethereum's, right? And so we've modified this underlying account system so that it uses all the actions that you do on Moonbeam are actually using Ethereum-style accounts, and actually using the precompiles will allow you to use your regular MetaMask wallet, Ledger, Trezor to do things like on-chain governance and staking and so on. And last but not least, we like to brag, or we like to talk about the sort of Ethereum dev-like environment that we've built on Moonbeam. You have tools like Chainlink, the Graph, Covalent, a friendly fork of Gnosis, and sort of all these tools that developers expect out of like an Ethereum environment. And so Moonbeam has all those so that developers can start building using these primitives that are basically super essential for building smart contracts on an EVM chain. For example, another one that I forgot to mention is Etherscan, which is really, really important for development. But that's it. I mean, that's the intro that I have for you today on Moonbeam. So let's jump right into how do we offer Ethereum compatibility on a substrate-based chain? And I've talked about this before, but I feel that it's important to touch again on these concepts because we're going to talk a little bit about into more detail about how they play a role in sort of this sort of precompiles smart contracts. So to understand sort of like how the Ethereum JSON RPC works, it's important to understand that this is the basic communication layer between a tool such as MetaMask or Truffle or Hardhat and an Ethereum node. Okay, so basically when the MetaMask wallet wants to know the balance of an Ethereum user, basically it does a request through a JSON RPC request to the Ethereum node with a certain structure. The Ethereum node understands this request that it's basically, hey, I want to know the balance of this account, in a more sort of like programmatic way. And then the Ethereum node will respond with a data structure that the tool, in this case MetaMask, understands, right? And so that is basically the path of a request from an Ethereum tool to an Ethereum node and then back to that Ethereum tool. And sort of it makes this sort of like communication layer that tools and the Ethereum nodes can interact with. How this works on Moonbeam, it's a little bit different because we don't have, our technology is based in Substrate, so we don't have this Go Ethereum or Geth client that it's just like natively support all these Ethereum JSON RPC calls. So the way that this works on Moonbeam is through this Ethereum compatibility layer called Frontier. And Frontier has multiple elements. And Frontier, it's a parity project, but we've worked really close and we put a lot of effort into this sort of project or palette because it's the core sort of like foundation of our technology, of our Ethereum compatibility technology. And so any Ethereum JSON RPC that comes from any tool or any direct JSON RPC call basically lands on this Frontier RPC extension. And the way that I like to see it is that it's sort of like a middleman. It's like a translation layer between this language that Substrate does not speak, which is basically this Ethereum JSON RPC, and Substrate runtime calls or things that Substrate understands, right? So, for example, once again, if we're talking about balance, Ethereum will request a balance in a certain way. Frontier will say, okay, Substrate does not understand this language. I'm just going to translate that call to Substrate, something that Substrate understands, and then the response that I'm going to provide through Ethereum JSON RPC is going to be structured so that tool understands it. Frontier, the RPC extension works together with the Palette Ethereum, and the Palette Ethereum emulates block processing, logs, and dispatches everything to the EVM backend. Palette Ethereum is also very important because it does all the signature checking and so on. And so once that everything is checked, is going to be moved forward to the Palette EVM, which is basically an access layer or another middleman between sort of this Substrate runtime, Substrate-based chain runtime, and the EVM implementation that we have in Rust, right? So it's sort of like a way to prepare everything to invoke the EVM and then calculate the state transition in the EVM. All right. So this is very high level, and some concepts might not be strictly like straight, but the idea is to understand that there's like a very detailed path from a JSON RPC call to the Rust EVM and back to these palettes into a response to the tool. I brought some examples, right? So for example, if I go to the terminal, Linux terminal or whatever, this is a typical curl command that you can do to send a JSON RPC request to a node. In this case, as you can see here on the second line, it's a Moonbase Alpha endpoint. And so basically the JSON load that we're sending, as you can see here, is basically calling the method ETHGetBalance. And this is once again the method that it's used to fetch the balance of a given account. And it is broadly used by wallets and so on. And so the way that this works is that when this request is done to the Moonbase Alpha node, the response that is provided by the Moonbase Alpha node is the following JSON object that you see here. And that might not make sense to you guys as a developer, but because for a human being, this number does not represent anything, right? If I tell you that your balance is 0x2b35323, this doesn't make sense. But this is because this balance is represented in hexadecimal numbers, And using tools, you can easily transform that number into a decimal number that it can be displayed nicely by, for example, MetaMask, right? So this is one of the JSON RPC calls that is done by MetaMask directly to represent the balance of an account at a given block, for example. And understanding this is really mind-blowing, because at a core layer, this is how all Ethereum tools sort of work, right? If you're ever programming in Ether.js or Remix, what's happening underneath that you don't see as a developer are all these Ethereum JSON RPC calls that are, a gazillion basically, just to be able to send a transaction, to get a balance, and so on. And so the way that Moonbeam works is that if we're able to understand that JSON RPC call and respond to it the way that the tool expects, that tool should work directly with Moonbeam. A more in-depth example here is sort of like at a node level. So this on the right-hand side is the logs of a Moonbeam node. And you can see here that once again, this is MetaMask. And one of the requests that MetaMask is doing, because there's actually a bunch, it's shown here with this trace request, where you can see an ID of 83 whatever, and then the method is ETH_get_balance, and the parameters are the address and the block number. And then the node actually responds right after with this response, as you can see that it's highlighted in magenta with the bug, JSON RPC 2.0. The ID matches to that of the ID of the request, so that it makes sense that this is this response is for this request, and the result is basically this hexadecimal numbers that is displayed in MetaMask nicely as a decimal number that represents something to the user. Okay, cool. So I've mentioned before when I was explaining Moonbeams, EVM with expanded features, right? And this sounds really fancy, but the idea here is to show you guys what do I mean with expanded features. And the answer is basically precompiles. So make sure that if you have, like I said before, any questions, use the Ask a Question button, and I'm happy to answer any questions at any point. What are precompiles, right? So in order to understand precompiles, we have to understand sort of like from a JSON RPC request, what happens in Moonbeam, and then we'll land at a precompile at some point, right? So let's say that the request that is received by Moonbeam is one called ETH send raw transaction. And this is the request that a Moonbeam node or an Ethereum node receives when with a signed transaction, right? I want to send funds to Kevin. I want to send funds to anyone, Alan in the audience or whatever. So the node will receive a signed transaction with the parameters to actually send the funds, right? What's going to happen next is that Frontier is going to grab that JSON RPC call, and it's going to work with Pallet Ethereum to make sure that everything is correct. And it's going to then call or interact with the Pallet EVM to then interact with the Rust EVM, okay? And so that is sort of the path of this request, without going into too much detail what happens in each step, to the Rust EVM. And the Rust EVM is going to use a function called transact call. And so this function, this Rust function in the Rust EVM is basically the function to execute a call. I mean, there's no real, the name is pretty straightforward. And it does a little bit of call initialization and checks. You can check the relevant code here that I've linked in the slides if you're more interested into what it's doing. But at some point inside that function, we're going to go into call inner. So that is another function that it's inside or nested in the transact call. The call inner, besides other things, I'm overly simplifying it. One of the things that it does is that it's going to check if the address that we're targeting with that call is to a precompile, right? If such, it's going to execute that transaction through the precompile logic. But if not, it's going to execute it opcode by opcode, right? So it's going to run each opcode through, let's say, the EVM, and then it's going to say, okay, this opcode does this. I'm going to jump in here in memory. I'm going to do this, transactions or whatever, and then I'm going to do this and that. So it's going to map through every single opcode. It's going to transact through those opcodes. But what happens if it's a precompile? What's going to happen is that it's going to go through the precompile execution, basically. And precompiles at the end, what they are helpers that live inside the WASM blob or the state transition function, but they are actually outside of the EVM, right? So you can think of the EVM as another state transition function. So let's say like a machine that actually helps you calculate a change in state. So, for example, if I send one token to Alan, the new state is that Alan has one token and I have one token less. So, but in the case of precompiles, they are actually, like the word says, precompiled, right? So the state transition that they create, let's say, are really precompiled and they live outside of the EVM. Okay, and so the idea is that the call inner will call that precompile execution or that substate transition function, and then what's going to happen is that depending on the response or the result of that execution of the precompile, it's going to roll back pallet to pallet Ethereum and Frontier, and then that is going to create basically a transaction receipt that is going to be shipped back through a JSON RPC response to the tool or to the development tool or wallet or whatever it is, right? So this is sort of like the happy path of a call to a precompile, right? The main difference, if it's not a precompile, is that on this line here, we'll do the opcode by opcode execution of the function call. Cool. So currently available precompiles, all right? So there are a bunch of them, and actually you might be using them without not even knowing if you're, for example, staking on the Moonbeam dApp. So the first is actually that I want to bring is staking precompile. So the idea is that it's a precompile interface, a Solidity interface, that helps stake tokens through the Ethereum API. So this is why, even though staking, it's a function that it's programmed in Substrate, you can actually use the Moonbeam dApp to, for example, stake to a given collator using the Ethereum API, which actually means just using MetaMask or Ledger or whatever Ethereum wallet you normally use. But this is all powered by the Ethereum, the staking precompile. So one way you can also see precompiles is that they actually help you call substrate functions, right? Which is not entirely true, but it's a way that you can think of it. Another precompile is the democracy one. As you can see right here, this user is voting on on-chain democracy proposals. This is in Polkadot. But this on-chain democracy proposal, you're actually participating in democracy through the Ethereum API once again, right? So this allows tools like the one shown in the video that it should replay quite soon. This is a tool called Polkadot, and you can see how a user can actually vote on this proposal using MetaMask as a wallet, right? So, for example, if you're building a dApp that is focused on democracy, you can have this sort of experience as well through the democracy precompile. Next is the ERC20 precompile that allows developers to access the native tokens of Moonbeam, Moonriver, and Moonbase Alpha, that it's Glimmer, Mover, and Dev, through a regular ERC20 interface. So this removes the necessity of having a wrapped Glimmer contract, wrapped Mover contract, right? You can don't need to wrap it because you can add this like token contract to MetaMask as I'm doing here in this video on the right-hand side, right? I'm adding the precompile address contract, and you can see that the token is called Glimmer, and I have exactly the same balance as my MetaMask balance is showing. And you can send it as an ERC20 and so on. And last but not least, for this first set of precompiles is a batch precompile that allows you to, as the name suggests, batch EVM calls into one single transaction. This is either atomically or not. I'm not going to go through it because I'm actually going to go into a lot more detail later on in the session. But the idea is that, if you have multiple EVM subcalls, you can batch them in one single transaction, keeping the message sender, which is really important. There are other precompiles that I did not cover here. For example, we have a crowd loan rewards precompile that allows users, as you might have done in the past, to claim your crowd loan rewards using MetaMask. We have call permits that we'll probably do a workshop in the future, author mapping, and others, right? So I just covered the main ones here. And actually, I have more precompiles for you because, like I said before, we actually expand the EVM features with this precompiled contract. So that's why we've actually, programmed a bunch. Now we have precompiles that are XCM focused. So the focus is on XCM and interoperability. The one that you might already interacted with without not knowing is the XC20s. So XC20s allows user or developers to interact with native Substrate interoperable assets through an expanded ERC20 interface. So, for example, if you've ever used XE.dot or XEKSM, which is Polkadot or Kusama's represented on Moonbeam or Moonriver. These are XE20s, right? You can add them to MetaMask. You can send them as an ERC20. You can add liquidity as you would with any other DEX on Stella Swap, SolarBeam, any other DEX that it's available on the network. You can use stake them through Lido. So XE20s allows any substrate asset, being Polkadot, Kusama, Akala, AUSD, Remark, to act or feel like an ERC20 on Moonbeam. And this is really powerful because developers are familiar with ERC20s and they're not familiar with substrate assets. Another precompile is the X tokens, and this allows developers or users to send XE20s to other chains in the Polkadot and Kusama ecosystem through the Ethereum API. So that is why, for example, when you're using the Lido interface to send XE.dots to Polkadot, you sign this with MetaMask, right? And this is really powerful because we have seen dApps integrating the functionalities, or wallets integrating the functionalities of sending XE20s to other chains using basically this precompile. And last but not least, the XEM transactor, and this is one of the newest ones that I'm excited the most. And it allows you to remotely transact, and I'm quoting myself, in other chains, because the transact that you can do sometimes is limited. What this means is that this is actually what Lido is doing on Moonriver and Moonbeam, to be able to, for example, you can stake your XEKSM or XE.dots on the Polkadot and Kusama. So you can do Polkadot and Kusama staking, but the action is initiated by you on Moonbeam or Moonriver. So, for example, a user that holds XEKSM on Moonriver can use their wallet like MetaMask or Ledger or Trust or whatever other Ethereum-compatible wallet to interact with the Lido contracts. And then the Lido contracts will mint a stake derivative, right? So in this case, it's STKSM, send it to the user. But more importantly here, the Lido contracts will actually use this XEM precompile called XEM transactor to do a remote call to Kusama. So this is now interoperability, native interoperability, from a smart contract that lives on Moonbeam or Moonriver in this case, directly to the Kusama relay chain. And this call will actually allow, it's basically saying, hey, Kusama, I want to stake XYZ tokens to XYZ validator, right? So this is really cool if you think about it, that an action on Moonriver is resulting in a staking on another blockchain. And we'll see more and more interoperability scenarios pop up, I'm sure. So the idea of all these precompiles and everything that I've showed before, and in Moonbeam in general, is the idea of connected contracts. And so the main focus here is that we want Moonbeam to be sort of like an Ethereum-compatible hub for interoperability, right? This is within the Polkadot ecosystem, but also outside of the Polkadot ecosystem. So, for example, we want to be a hub for interoperability for projects that can build natively on Moonbeam and then use sort of other parachains in the ecosystem for services like oracles, storage, identity, but also connect through other technologies like Axelars or Nomads bridges to other blockchains in the ecosystem to expand functionalities, right? So you can have, for example, a DEX that has all the liquidity concentrated on Moonbeam, but then, it has sort of like other deployments on other chains that has minimal logic to handle, swapping and so on, bringing the liquidity to Moonbeam. So the idea of connected contracts is that Moonbeam can be this hub for interoperability, but more importantly, not only within Polkadot ecosystem, but also with other chains, and then create this sort of like services that users won't really see what's happening underneath. Interoperability will be a given basically for users, and developers will build this really cool interoperable sort of dApps that will do everything for the users. All right, so let's go into the precompile, the batch precompile demo. And if you've ever built on Ethereum, I think you'll actually end up thinking, hopefully, that this is a really cool feature, right? And so the demo that I'm going to do here, part of it is in this GitHub repo. This is the part that I'm going to show the last with the Ether.js code and hard hat and so on. But there's a part that is going to be in Remix that I did not put on the repo, even though it's fairly similar. But before we go into the demo, let's talk a little bit about the batch precompile, right? And so, as I mentioned before, the batch precompile, batch EVM subcalls into one transaction, and the message sender is maintained, right? This is really important because if, for example, you use multi-call, then the message sender might not be maintained, and so this is something that is important. It provides three main functions and two events, right? So the two events that I'm showing on the right-hand side, they're always sort of the same events over and over, right? So they don't really change, even though I'm going to show them multiple times. The first function is called batch sum, and the idea is that you're going to batch a bunch of transactions, but if one of the subcalls fail, the following subcalls are still attempted, right? So if you do 10 subcalls and number 5 fails, the function is still going to try to do 1 through 10, right? So only 1 fails, that's fine, but the other 9 actually succeeded, let's say. The important thing is that the two events that you can see right here is that one of them is emitted and it has its own signature, basically, if the actual call was successful. And then it will show you here which call was successful. And then the other event is emitted when the subcall failed, right? So for example, in this case, we'll see 9 events of subcall succeeded and 1 event of subcall failed, with the index here being 5, right? The next function is batch sum until failure. Once again, the idea here is to batch transactions. That's going to be repetitive. But the main difference here is that if one of the subcalls fails, no further subcalls are attempted, right? So if we go back to our example before, if we're doing 1 through 10 and transaction number 5 fails, then 1 through 4 will actually be successful, but then we're not going to attempt 5 through 10. So they're gonna basically just not go through. All right. And so, the idea is to provide all the different like sort of tooling for users to play around with this. There might be certain scenarios that you want this like batch sum until failure, but there might be some scenarios that you just want to batch them all. Doesn't matter if one of them reverts. Last but not least, this is really cool because the batch all, as its name suggests, allows you to batch transactions atomically, meaning that if none of them, if one of them reverts, all of them are actually reverting. Okay, so this is atomically, meaning that all of them have to succeed in order for the batch to succeed, right? And so these are the three main functions, and like each of them have the core basic functionality of batching transactions, but they have different rules, sort of like what will happen if one fails, what will happen if one succeeds, and so on. The other thing that I've not explained yet is the different input parameters, right? We have 2, we have value, we have call data, and we have gas limit. And they're exactly the same for all 3 functions. So each of the parameters have a different meaning, right? The 2 is basically the list of addresses that we're going to do for each subcall, right? So it could be either a smart contract address if we want to interact with a smart contract, or it could also be an account address if we want to, for example, send native tokens to multiple addresses. And it could be a mix as well. It doesn't have to be one or the other. And there must be 1 address per subcall. So even if you're doing, for example, multiple subcalls to one single contract, you have to put it repeatedly there so that the precompile understands that there are, like, for example, 10 calls to the same contract, okay? The next input is value. And as you might suggest, this comes from the JSON transaction object value. And in this case, it's basically a list of value that you're sending for each subcall. And this is a UN256 array. So this is just basically an array of the amount of tokens, or in this case, dev, glimmer, or mover, that you're sending with that subcall. An important thing to note is that if the array is shorter than the to array of the address array here at the top, additional calls are done with value of 0, right? So if you're doing 10 subcalls and you don't want to pass any values, you can just put an empty array, and that is going to be basically that each subcall is with a value of 0. The third element is a call data. This is really important because, once again, this is the call data for each to address or each to interaction that we're doing. This is necessary if you're interacting with smart contracts. If you're sending tokens, you don't need to provide, native tokens, you don't need to provide any call data. And as before with the value element, if the array is shorter than the to array, then additional calls are done with no call data, right? So for example, let's say our first subcall is a contract interaction. We have to provide a call data. But our second call is basically we're sending def to someone, right? So the second element in the array could be just basically nothing. Like we can just provide an array of size 1, or we can just put an empty element here, and that will also be sufficient. Last but not least, we have the gas limit. And as you might imagine, it's the gas limit for each subcall that we're doing, right? It's for each to-address subcall, basically. You can use 0 to forward all the remaining gas to the next subcall. And if the array is shorter than the to array, all remaining gas is forwarded, right? So for example, in this demos that I'm going to do, I'm always putting empty brackets, meaning that I'm just going to forward whatever gas was estimated and used for the first one. I'm going to forward it for the second one, third one, and so on, right? If you want to play around with gas limits, you can do it as well. I want the first subcall to use a maximum of 100, the second one to use a maximum of 30, and so on, right? But it's up to you to decide what to do with this. So hopefully this is clear, because I'm going to go now to the demo, and I want to make sure that you guys understand each of the input parameters that you have to provide for the batch precompile, all right? So I think I don't have any more slides. I can jump directly into the demo. So what I have right now, for purposes of speed, I could have done this on Moonbase Alpha, but I have basically a Moonbeam development node down here. As you can see, it's producing blocks nicely. We're up to 411 blocks. So what I'm going to do now is that I'm going to jump into Remix. Let me bring this up. Cool. So you can see that I have MetaMask connected to this node, this Moonbeam dev node that I'm running. And I also have Remix right here that I have connected basically to my local node using the injected Web3 environment, okay? So as you can see here, this is the batch precompile interface. So you have the 3 functions that I've mentioned before: batch sum until failure, and batch all, and the 2 events that we've mentioned before. They have a different signature, basically, because they're different. And then we have the 3 functions. So the first thing that I'm going to do is that I'm going to grab the address of the precompile that it's here, and I'm going to load it into the Remix interface, right? So in order to do that, you have to make sure that you have the batch open, the batch precompile contract open. You grab the address, you put it here in @address, making sure that you have the environment set as injected a Web3 and MetaMask or your Web3 provider connected to the network that you're testing against. And so if I do this, I see the batch precompile interface here at the bottom with my 3 functions down here. So the first example that I want to do is to transfer dev tokens to Alice and Bob. But the cool thing is that I'm going to do both interactions in one single transaction. I'm going to sign once, but I'm going to send dev tokens or testnet tokens to Alice and Bob, right? So if we remember correctly, the 2 is basically the addresses that we're going to interact with, or we're going to interact with at the end. So this is going to be basically Alice's address, right? And the second one is going to be Bob's address, right? And for value, we actually have to say, okay, how many dev tokens we want to send to Alice, and how many dev tokens we want to send to Bob. They don't have to be the same. They could be different. If I do, for example, 1 dev token, and I put here, and I only put 1 dev token, I'm going to send 1 dev to Alice, but I'm going to send 0 to Bob, right? Because the size have to match if we want to send, for example, 1 and 1. I could, for example, I can do 2 here, and I can do 1 dev token to Bob, right? And then for call data, because we're not interacting with any smart contract, we can just go ahead and just put an empty array, right? Because we are not passing any call data. For gas limit, we can do the same. We can either put, whatever gas we want for each subcall, but for the sake of simplicity, we can just put an empty array, and that's it, okay? So let's build this. I mean, we cannot pass this because this doesn't make any sense. So in here, I'm going to need to provide basically the Bob's address and Alice's address. And in order to do that, I'm going to go to MetaMask. I'm going to go to Alice, copy her address, go to Remix and paste it. And then I'm going to go back to MetaMask. You can see that Alice has 0 dev, so it's not like I'm cheating. I have Bob copied here and pasted here. Cool. For the value, I need to provide the amount of tokens that I am going to pass. So in order to do this, you need to provide it in the minimum unit, which is, as you might have guessed, is way. So I use this little tool here all the time where you can just, I'm just lazy adding zeros manually. So I just put here that I'm passing 1 Ether, which is sort of the same units as 1 dev. It has the same zeros. So I can just copy this value in way and then just put here 1 and 1. I'm going to change this 1 to 2 because we're sending 2 dev tokens to Alice and 1 dev token to Bob. And that's it. We have built our batch precompile interaction. I'm going to use the batch all because why not? So I'm just going to go ahead and copy this line here. I'm going to copy this line here, and then I can just pass empty arrays. And I should be ready to go. Hopefully this works. Let's see. So I'm going to transact. It's failing out of, I know why, because I have Bob selected and Bob has no funds. So I have to go back and select Gerald, which has plenty of funds. So you can see here that I have Gerald with a lot of funds. And I'm going to go up down here and click again. I do have my MetaMask pop-up, which looks awful because I'm super zoomed in. So I'm going to click confirm. And as you can see, I should get a confirmation. And if I go to MetaMask, Alice has now 2 dev tokens and Bob has 1 dev tokens. Everything with one single transaction, which is the main cool thing about the batch precompile. If I go to this nifty explorer that I have here, I can go into the block and I can check the transaction hash. And then I can just click here on view raw. And this is going to show me sort of like the raw tracing of the transaction. And what I want to show you in the transaction receipt, let me zoom in. All right. What I want to show you in the transaction receipt is that I should have 2 logs. So one of them is for the first subcall, right? And you can see the topic is, sorry about that. The first topic is BF85, right? And you can see here that in data, we have the index of the subcall, which is 0. This is Alice's transfer, that it was successful, basically. And then the other subcall is basically the index 1, so the Bob's subcall. And then we can see down here that it was successful by checking the event signature, which is BF855484. All right. So in this case, we did a batch all that was atomically executed. And in one single transaction, as you can see, because I only have 1 transaction hash, I have actual 2 balance transfers, 1 to Alice and 1 to Bob. So that's a cool thing about the precompile. All right, I brought another example that it's a little bit more complex, but it'll still be quite high level, right? And it's a make pizza example, all right? So it includes 2 contracts. So the first contract is basically an ERC20 token that I've named pizza token, and I've minted 1,000 pizza tokens. And the other contract is called make pizza, and the idea of this contract is that it will check if the actual sender has more than 1 pizza token. And it will also check that there's an allowance, correct allowance, right? So if you remember ERC20s, they have the allowance option, which allows external users or contracts to spend tokens on your behalf or transfer tokens on your behalf. And so this is a typical thing when you go to a DEX and you want to do a swap. They ask you to approve first the allowance so they can transfer these tokens out of your wallet for you, right? So we have 2 requirements. The user has to have enough pizza tokens to make a pizza, and the user has to set the allowance correctly to be at least of more or equal than 1 pizza token in order to have this contract right here, the make pizza contract, transfer pizza tokens on the user's behalf, right? And then what we have to count the number of pizzas that we've created, we have a pizza counter that gets increased every time the make pizza function gets called. It is very, very simple. So let's deploy first the pizza token. So I'm going to deploy it. MetaMask just looks awful when it's so zoomed in. And then the second thing that I'm going to do is copy the pizza token address because I'll need it for the make pizza contract. So I'll go here. I'm going to deploy the make pizza contract, but I need to have the pizza token address. So I'll paste it there. and then I'm gonna deploy the make pizza contract. Cool. All right, so what is the idea that I'm gonna do, right? If I were to actually interact with the make pizza contract, I would have to go to the pizza token and manually approve it here. So I have to do a manual approval where I say, okay, the spender is a make pizza contract, and the amount that I am allowing that contract to spend is whatever, right? But using the batch precompile, we can actually do both transactions, so the approval and the make pizza function in one single go or one single signature, right? So right now, if I try to go with make pizza contract and I try to make pizza, I'm going to get a revert. I don't know if you can read this very well, but it's saying you don't have enough pizza allowance, right? So I need to do the approval part first before actually doing the transfer from on the later on, right? But yeah, we can fix this really easily. The hard way would be to actually, like I said before, approving manually. So I have to sign one transaction for the approval and sign one transaction for the make pizza. But the other way I could do this is using the batch precompile, all right? So that is basically the example that I have here. So let's build the input together, right? So the first element is the first interaction that I want to do. It's the approval, right? Actually, let's actually build the call data first, because that will help us actually understand which contract we want to interact with. So the first interaction that I want to do is approve make pizza as an pizza token spender, right? And the second interaction is make pizza, right? So the approval actually goes in the ERC20 token contract. So the first two has to be the ERC20 token, right? And the second interaction is directly in the make pizza contract. Note that for this particular interaction, we don't need to provide a value. We don't need to send dev tokens to anything. And the gas limit can stay as an empty array because it's not really necessary. So let's build this, right? So the first thing I'm going to copy, it's a pizza token address, and I'm going to put it here at the top. The second element that I'm going to do is copy the make pizza token contract, and I'm going to put it here because the first subcall is going to be against the ERC20 token, so I can approve the actual make pizza contract to transfer the pizza tokens, right? And the second interaction is going to be against the make pizza contract, so I can make pizza. All right, so we need to calculate or get the call data, and this is probably one of the hardest parts, until you get used to it. So the easiest way to do it, there are multiple ways to do this, but the easiest way probably here in Remix is to actually fill out the information here and then just use this copy button here. So what I need to provide is basically the amount that the spender, which is going to be my make pizza token contract, my make pizza contract, and the amount that I'm going to approve in order for the contract to spend, which is going to be 1 basically. I'm gonna put 18 zeros, but I need to basically, I'm approving the make pizza contract to spend 1 ERC20 on my behalf. Okay, but I'm not going to do transact, because if I do transact, I'll need to sign a transaction. But what I'm going to do, just copy this, and this is going to be my call data here. It's going to look really, really long, but the call data is basically what is called the function selector or the function signature. And then the elements here, this is basically the make pizza token, make pizza contract address. And this is 1 times 10 to the 18th for decimals in hexadecimal, all right? In order to get the function signature for make pizza or the call data, it's a little bit more problematic because of I would say it's a bug or an error in Remix, in where you don't have the copy button here to get this make pizza call data, right? There are a couple of ways you can actually get the actual call data. One of them is actually clicking here. This is going to have an error. You can send a transaction. But instead of signing the transaction in MetaMask, we can actually go ahead and click here in Hex. And this is actually the call data of this transaction, right? So I can copy it from here and then reject the transaction and then paste it here, okay? Let me make sure that I did not mess it up. All right, so you can see that the call data, it's 5 BBB, blah, 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 right? So 3 Bs. The other way to actually get this call data is that you can go to a catchhack 256 hash calculation function and basically do it here and put the function name, make pizza, right? And then basically, if you have any inputs to the function, you'll have to put them here, right? So for example, if it's a UN256, you have to put it here. If it's an address, you put it here. But in the case of the make pizza function, it's only make pizza without inputs. And you can see that the first 8 hexadecimal characters or 4 bytes is actually the function selector. So this is how this works. But I already have it. I can compare it if you want. But here you can see that it's 5 BBB 4D81. And then here you have 5 BBB 4D81. All right. Cool. So I have my call data already calculated. So I can go ahead and go to the batch precompile. Let's delete all this from a previous example and fill this out. So I'm going to put the 2. I'm going to put empty for value. I'm going to go ahead and copy the call data. Hopefully this gets copied correctly. I don't think it did. No, it did not. Let me try it once again. Oh, I'm just going to do it manually. All right. And then I can put empty here, right? Okay, so what's going to happen, right? What's going to happen is that if we go to the pizza, make pizza contract, we have not made any pizzas, right? And the contract pizza token balance is 0. What's going to happen now is that in one call, we're going to do the approval and the transfer of the token, and we're going to make a pizza, so the counter will increase to 1, and then the actual make pizza contract will have a pizza token balance. All right. So I'm going to go ahead and transact. I'm going to sign this transaction and confirm. And then we get a confirmation. Let's go to Moonbeam Basic Explorer once again to confirm that we have a transaction here. If we click on the block number, click on the transaction hash and click on view raw, we will definitely see once again, even though this is not great, we will definitely see 2 events. So one of them is for the subcall 0, as you can see here, and then this is a successful subcall. And then down here we have another one for this is actually the token transfer event, the approval event. Sorry, and then next we have the token transfer event, and then we should have at some point the successful subcall 2, as you can see here. So there are 4 events, 1 for the approval, 1 for the token transfer, and then the other 2 for the subcalls being successful. If I go back to Remix, you can see that the token has now, the contract has now a token balance, and pizza counter, it's 1. And that's it. I mean, you now more or less should understand how to work with the make pizza, the batch precompile. I think I'm hungry, then I'm always saying pizza. But let's do a little bit more. And because we still have 10 minutes, you have not asked any questions at this time. So let's go ahead and do a little bit of how you would use a batch precompile on a library like Ether.js, right? So I do have this here. This is the GitHub profile, the GitHub repo that I shared with you guys. As you can see here, I have the contract, the same contracts, ERC20, make pizza, and batch. And I already deployed. I have the deployment script there that you can see that it has, deploys the pizza token, and deploys the make pizza token contract using the pizza token address and so on. So actually what we'll do now is that I'm going to actually deploy the tokens and the contracts because I've not done this now. So I created some scripts in the package.json files to make it simple. So you can see here that I'm running npx hardhat run, the deployment script in the network def, which is basically my local Moonbase Alpha node. And you can see here that the pizza token was deployed. This is a separate pizza token. It was deployed to this address, and the make pizza contract was deployed to this other address. All right. So I have included the same sort of examples that I've done before. I have the one example to send dev tokens to Alice and Bob, and one example with the make pizza sort of like, example. And so in the send dev tokens, I've basically defined Alice and Bob's addresses and transfer amounts. So you can see that for Alice, we're going to transfer 2. For Bob, we're going to transfer 1. Excuse me. We actually print the balance of Alice and Bob before the transfer. And the next part is basically the trick, right? So we actually have the batch precompile interface here. So we can use the hard hat runtime environment, ethers get contract add, and then use batch. And then this is the batch contract, and this is the batch address. So this is where the batch is living, basically. And then this will load sort of like a batch contract interface. And then we can just basically call the functions like you would with any other contract on Ether.js, where we actually, in this case, we're doing the batch all. And as you can see before, we're providing Alice's and Bob address as an array. We're providing the value of each token transfer as an array, and then the call data and the gas limit as empty arrays. We have now here an await, just to await for the transaction to go through, and then we're printing the token balance, all right? So let's run this example. This is with yarn, send def. Once again, this is npx hard hat run, the send def JavaScript file, and then network def. So you can see that the balance, Alice's and Bob balance is what was 2 and 1. I've sent the batch transaction, only 1 transaction, as you can see here, only 1. And then after I have Alice's and Bob's balance being 4 and 2, all right? For the make pizza example, it's a little bit of the same. I am loading the batch contract, the pizza token contract, and the make pizza contract. And then I'm printing how many pizzas we've made, which is going to be 0 for the first time. What I'm doing here, and this is the tricky part, is that we need to calculate the call data, right? And the way that you can do this with ethers, at least, it's by calling the contract. And before calling the function, you can actually do populate transaction, right? And what this is going to do is that it's going to populate the transaction, in this case, a TX variable, as an Ethereum transaction object where you have a to, a gas, a nonce, and whatever. And so basically what we're doing afterwards is that we're retrieving the call data by using the transaction.data, basically key, all right? So that is how we retrieve the call data in a more programmatic way and not via remix. We can do exactly the same as we did before for the make pizza. So we could do it, the Ketchak 256 way, which is a little bit more complicated, or you can use the populate transaction method and then just grab it from the transaction.data element, okay? But this is entirely the same as we did before in Remix when we fill out the information and click the copy button there. And then we're gonna build our batch transaction, which is only 1, even though I have it in plural here. But you have basically the batch contract, batch all. So this is an actual transaction that is going to be signed and sent. And then we're building our inputs as we did before, right? We have the addresses first, the empty array second, the call data third, and this is for the token, and this is for the make pizza contract, and the gas an empty array, right? We're sending the transaction, and then we're going to print the pizza counts just to show you that with one interaction, we actually did the approval and the minting of a new pizza, let's say. So if I do yarn make pizza, you will see that this is running this file. And we can see that there's 0 pizzas currently. This is going to do the batch transaction with the following hash. And then you have currently 1 pizza, right? If I run this again, we're going to have 1 pizza. I'm going to mint again another pizza using an approval and a make pizza call. And then we can keep going. But I mean, 2 calls is not really that great. You have to think about this works for 10 calls or 20 calls, depending on the gas. But this is where you can truly exploit this, to improve the user experience in general. But yeah, I mean, this example is in the link that I showed you before in the presentation. So hopefully you check it out. I don't see any questions up to this point on the ask a question button. So if there are no further questions, I think we're almost there in terms of time. So feel free, you can find today's presentation in this QR code here or in this bit.ly link, Moonbuilders Batch 2022. If you want to contact us, make sure that you reach out, you check out our website. There are a lot more social channels there. You have our documentation side. Telegram and Discord are great places to get in contact with us. And you can follow us on Twitter as well at Moonbeam.network. Thanks a lot for joining the session. And hopefully, if you're watching in the future, this is helpful for you guys as well. And yeah, I mean, tune in for the next Moonbuilders workshop. So yeah, thanks a lot for tuning in.